All right. So I'm going to talk a little bit more specifically about what we have at 6BMB Beamline. So you'll notice that I have in bold here, Diane. That's Diane right there. She is the lead scientist for 6BMB, and she is the person that knows the machinery here inside and out and can help develop new experiments and things like that. So she's a very good person to talk to if you have any questions or ideas that you want to discuss. So there's a lot of different things that you've seen and will see and will hear. So I just wanted to say that the program that I run is the Stonybrook Multi-Angle X-ray program through SEAS, which, as Andy introduced, is the Synchrotron Earth and Environmental Science organization. SB Max is Stonybrook Multi-Angle X-ray. 6BMB is the beamline that we're going to be talking about here. I also run a monochromatic facility at Brookhaven Lab at the National Synchrotron Light Source 2. That is called MaxPD, which stands for Multi-Angle X-ray Powder Diffraction, which is an end station at the XPD beamline there. And we also do some stuff in the high energy engineering X-ray beamline X that Andy can share here as well. So we do all kinds of different science at these facilities. There's a lot of different things that we're capable of studying. What we're going to be focusing on today, obviously, is rock deformation, rock mechanics, and the associated things. So to talk just a little bit, and as Tim said, we're going to be saying a lot of the same things over and over again over the next couple of days. This is exactly where that's going to start. So pressure is force divided by area. So you can see these two blocks in two different orientations, even though they are the same size, exhibit a different amount of pressure on the surface in which they're sitting. That is the entire theory behind snowshoes, where you are distributing your force out over a larger area so you don't break through the snow or ice or whatever dangerous surface it is that you're walking on. Little interesting point of fact is that a 100-pound woman in stiletto heels exerts 20 times the amount of pressure on the ground than a 6,000-pound elephant, which is precisely why I stopped wearing stiletto heels. And they're very, very difficult to find in size 16 men's. So now I want to take everybody here, since you guys are already used to standing up, you guys are good at following orders. So just take your left arm and hold it out in front of you like that. Now take your right arm, squeeze it as hard as you can without leaving any marks, because I don't want to go to jail. And you've added now about a half a bar of pressure, not quite. So atmospheric pressure and 1 bar of pressure is essentially the same thing. And you've added not even half that again. So when we talk about high pressure, what we're going to be doing here, we're talking about a completely different scale of things. Now, rest in power, King. So if let's not talk about him, let's talk about the rock. The rock gives you a bear hug as hard as he can. Now we're talking about 5 to 7 bars worth of pressure, which is really tight and hurts a lot from experience. And still, imagine Bruce Lee were still alive and you managed to say something that really angered him for some unfortunate reason, and he decided to roundhouse kick you in the face. That would be 25 to 30 bars of pressure in the face. And it only takes about 12 bars of pressure to break bone. So now these are the types of pressures that we're going to be dealing with every day on the surface of our planet. But if we talk about pressure in not so relatable terms, and we go down to the depths of the Marianas Trench, that's about 1,100 bars of pressure, so 1,100 times atmospheric pressure. We go to the core mantle boundary, and that is 1.35 million bars of pressure. And at the center of the Earth, it's 3.6 million bars of pressure. So 3.6 million times the atmospheric pressure that we're used to. Now, in D-dia that we're talking about here, we're usually in the pressure range of up to about 120,000 times atmospheric pressure. As Tim says, you can go higher, but the trade-off is it makes it much more difficult and you're much more likely to break stuff, which we try not to do as often as possible. So I just want to give you a little bit of a handle on what the size things are that we deal with as well. This is my friend Haruka. She is standing in front of the 2,000-ton hydraulic press that we had at Ehime University in Matsuyama in Japan. And you can see her standing there. Notice where the bolts of the press are, just above her head there. And there's me standing. These two presses are right next to each other. there's me standing in front of the 3,000 ton press, and you notice the bolt is the same distance above my head that it is above hers. But I should point out that she and I have very different scales. So the 3,000 ton press is also built significantly into the floor, which the 2,000 ton press is not. So as you start to generate a lot of these large forces, things get bigger and bigger. The cell assemblies for these experiments are pretty small. That little thing right there in the palm of my hand is the large volume sample that we're talking about in these large volume presses. So this is just reinforcing what Tim was talking about earlier about, even though they are called large volume, they might not particularly be what you would be used to thinking of as large samples. So we have two different types of X-ray modes that we're going to be working with here in this workshop and between the two beam lines that we're going to be looking at. We have white X-ray beam at 6 BMV, which is an energy dispersive measurement. And we have all different sorts of synchrotron X-ray energies coming down the pipe to us. So we use everything from 20 to 100 keV in every experiment at all the times. So we have a huge amount of photons coming down the pipe at every energy of the synchrotron radiation that we're going to be using. So what this does, and I'll go into it a little bit a couple slides away from now, what's nice about this is it allows us to be able to use slits that are downstream from the sample to define the diffraction volume that we're looking at. So we have these cell assemblies like Tim showed that have all of these materials that help support the pressure around the sample. Well, using the white beam and the slits that are downstream, we can ignore everything that's around the sample and look at just the sample itself, which is really nice. Monochromatic beam, if you skip all the way to the bottom, unfortunately, means everything in the beam path diffracts. So no matter what is there, no matter where you are, it's going to show up on your detector. So that is one of the downsides. One of the upsides is that the energy is very precisely defined. So you get a very, very good, you can measure texture. There's all sorts of things that you can do with monochromatic beam that you can't do with white beam. There's all sorts of things you can do with white beam that you can't do with monochromatic beam. You're going to be doing both. So that's pretty cool. All right. So this all comes back to Bragg's law, and lambda equals 2d sine theta. So lambda is the X-ray wavelength. That's really important. Again, in monobeam experiments, it's defined. And in white beam, that's variable. Theta is the Bragg angle, which is the angle between the incident X-ray beam and the atomic planes in the sample. And then the d-spacing is what we care about, and that's the distance between the different successive planes of atoms. So you've seen something very similar to this in what Tim just showed. But we have, in this case, we have the X-ray beam coming in from the left. It's hitting a polycrystalline sample that is randomly oriented, and it causes those diffraction cones to come off, which are then collected on a flat detector there and show up as circles. So in a monochromatic experiment, the wavelength is fixed or known, and we're measuring the theta. This is an example of that. Again, we have our sample here. Shoot through, we can do the radiography measurements that Tim mentioned, where we are opening the slits up wide and we can take an actual photograph of the sample using a scintillator that lights up and really snazzy, sophisticated cameras. And then we have the X-ray diffraction patterns that are shown in the back, which Tim gave you an excellent example of, so I don't need to focus on at all. Now, in the white X-ray beam, we have the opposite situation. Our theta is going to be fixed or known. And what we're going to be measuring is the wavelength of the X-ray that hits the detector. So we have an energy dispersive detector that is it's a germanium crystal that's capable of measuring the energies of all of the photons that hit it and separating those into a bin. And that is what's going to give us those nice 1D diffraction patterns that we were looking at before. The one thing that we give away with this is we don't have that full ring like we get in monochromatic beam. We have our detectors oriented at specific angles here. So what we have is the X-ray beam coming in from the right. We have our sample here. And because it's all different energies and all of the crystals are diffracting everywhere, really what you have is a gigantic mess of X-rays going everywhere. So what we have here is two slits downstream that define a particular angle. They're called the conical slits because they form a cone that goes back to the sample. That cone is defined in our case as 6.5 degrees. So our 2 theta value is fixed in this experiment. Only X-rays that go off of the sample at 6.5 degrees will make it to the detector at the end. Everything else is blocked. So we've defined now what our theta is for these experiments. And just to show what I was talking about before, we have the detector behind these conical slits here. So we're able to define within our sample, which would be this cross section here, the circle, we're only looking at what can be seen by the detector. And the detector can only see what's defined by that cone. So all of the stuff here, all of the cube material that Tim showed earlier is all of this material here, and we can completely ignore it because the X-rays that we're going to be looking at only show us what's there. And at 6 p.m., in particular, we have 10 energy dispersive elements that are circularly distributed every 22.5 degrees along a half circle this way, and then at 270 degrees on the other side. That allows us to align the sample as well. And normally what we do is we collect the diffraction in these 9 detectors during the experiment. Sometimes we also do the other one, but usually just the 9. So this you're used to seeing. I don't have the movie version. I don't have the picture version. So what can I say? So you're used to seeing that. Now, talking a little bit about what we were talking about earlier, what Tim was mentioning, elastic deformation. You have a sample at ambient conditions, you squeeze on it pseudo-hydrostatically, it gets smaller. That makes sense. You release the pressure, it comes back to what it was before. Now, plastic deformation is a little bit of a different beast because you're not going to have pseudo-hydrostaticity anymore. You're adding more force in one direction versus the others, and that causes the sample to deform. And then when you release all of that stress and pressure, the sample is now no longer the same shape and size and as it was when you put it in. So that's the big difference between the elasticity and the plasticity that we're going to be measuring in these experiments. So if you remember this is what the X-ray diffraction is going to show us. So what this means is you've got a bunch of randomly oriented crystals. This is really, really super simple unit cell that we're looking at here. We're going to add the pressure. Unit cell gets smaller, rings get bigger, just like Tim just said. Now we're going to deform it. It's going to change its shape, and the rings become ellipses. That's what we're looking for in all of these experiments, whether it's monochromatic or white beam. So in particular, 6BMB, we are a white beam multi-angle facility. And again, we use 20 to 100 keV of the X-ray energies. We have a 10 element array of solid state germanium detectors that we just showed. We also do the X-radiographic imaging with the scintillator that Tim was talking about. It's the same identical setup. Ours is always in place because our gag is actually located inside the conical slit. So it is always in place, and all we have to do is just open and close the slits in order to go from diffraction to imaging mode. We run a 250-ton press down there. We have those differential hydraulic pumps, and it can be swapped out for other things. And it allows us to do some really cool steady state and dynamic stress studies. And we have an integrated acoustic velocity system, which is really cool. I'll talk a little bit about that. It's not something we're going to be using during the experiments during the workshop, but they can be incredibly useful for things that you might want to plan to do down the line. So one of the first things that we did here was we actually, a few years ago, had a Journal of Visualized Experiments article come out, and they actually came and filmed us, and we did the kind of tutorial about how some of this stuff goes. So if you want to see how some of these experiments are run, you're more than welcome to look it up. You can also, for bonus points, count the number of metal horns I managed to sneak in there. And you'll also see my soda makes a very important side appearance several places in the video as well. All right, so let's talk about the acoustic velocity measurements real quick. So what's really nice about these, this is the same setup that Tim showed, where you've got your sample at the center of the 6 dia angles. And we've got our X-ray diffraction, we've got our imaging, but we also can get some acoustic velocity measurements as well. So this directly measures a lot of different physical properties without the need for an internal pressure standard, and it provides important ground truth benchmarks against which lots of other techniques can be compared. So what's nice about these is it allows you to measure the shear properties of materials, which is not easily measured with other techniques. The diffraction gives us the unit cell volume. The unit cell volume gives us the density of the material. If we know the density, then the image itself gives us the sample length, and we can measure the P and S wave velocity or speeds, I should say, the travel times in the sample. And then the travel times and the image length gives us the velocities. Velocities and densities means you've measured the bulk modulus and the shear modulus at all of the different conditions of the experiment. So you don't need to actually fit for anything. You've actually measured all of that stuff. Can fit for stuff though. This is just showing, as we compress, you can see that the sample is definitely getting shorter. We can send in the ultrasonic signal and the different reflections. We can use the pulse echo overlap method, where literally we say, hey, here's one pulse, here's another one, and we'll line them up until they overline each other. And when they do, that's the travel time. So it's actually a fairly simple technique in that sense. And I'm going to warn you, this is where my eyes start to cross a little bit. There is lots of math that goes into it, but what you're really looking to pull out are those 6 parameters right there. And once you have those 6 parameters, you can model how a material behaves under any set of pressure and temperature conditions that you would like. And this is an example of that, iron silicide. And this is nice and pretty and kind of dates me, tells you how old I am. But that's a nice data set that we collected on the system that we have. At 6 p.m. So this system is nice because it's directly integrated with all of our control systems, so we can coordinate and get everything working together. That allows us, like previously, we couldn't automate it, coordinate data collection or anything like that. And usually ultrasonic experiments only used a single detector, so there was no information about any deviatoric stress that might have been on the sample. So this system is very nice because it collects all of the acoustic data in under a second. It's actually now 100 times faster than that. We can measure processes like melting and phase transitions as they occur now, where it used to take so long that we would only be able to see the before and after. And now we can actually watch as things change. And this has been fully integrated into the press controls, the EPIX controls. So you can do this on any experiment. And there is a next gen redesign that's in process. Stay tuned for that. It's going to be badass. All right. So now to bring in the deformation edge of things a little bit. These are the first experiments that we were doing where we were combining deformation with the ultrasonic experiments. And this is using a hybrid acoustic and deformation cell. This is Taryn. I believe that you may hear from her tomorrow during Pamela Burnley's presentation. She is amazing and does some really cool stuff that literally no one has ever done before. So she's kind of blazing a new trail with the mixture of these techniques in geosciences, which is very cool. So she's combining the deformation with ultrasonic acoustic velocity measurements, combining that with elastic plastic self-consistent modeling to determine the stresses and the strains on the sample, and seeing what comes out of it. So one of the first things that we were able to do was determine some of the acousto-elastic effects on olivines. And this is just a whole lot of things here. You can see this is the EPSC modeling that she will probably be able to tell you much better than I could. But you can see in the D-spacing, this is where the D-spacing, the peak would be normally. And then you have the compressional direction and the transverse direction. You can see that there's a difference. What that is the compressional direction is going to be your detector 1 vertically, and your transverse direction is going to be detector 5 horizontally. You can see they're in very different places as far as where the centroid of their peaks are. So she was able to find that there is a significant difference in the P waves that starts before you can actually start to see the deformation of the sample. The shear waves seem to remain pretty consistent the whole way through. But again, there will be probably more information on that tomorrow. So this is something that I think you guys are a little bit more familiar with. This is stuff that Caleb has done at 6 p.m. And Caleb and his group will be the people walking us through the sample preparation at 6 p.m. and putting together the cell assembly and doing a rock deformation experiment. This is just an example of what they were able to do here, where they were able to deform a biotite quartz plagioclase gneiss during melting and monitor the reaction changes with the increasing of the temperature. So when there's wet granite melting, the melt channels form parallel to the compression direction. So they can deform this way as he spins this way. But for dehydration melting, you end up with it forming along the foliation direction, which is independent of the actual compression direction. So that is one example. Another example of things that he was looking at involved the pressure dependence of dolomite creep, where you can see that there's about 10 orders of magnitude difference between wet olivine and the dolomite here. So this is important for subduction zone mechanics, earthquake, earthquake mechanisms, and whether or not they're going to happen at high pressure and high temperature. And what's really nice is having this workshop means that you guys can have ideas for your own experiments and you can decide to apply for beam time. What's also really nice is that this workshop specifically has time set aside on Wednesday to discuss your ideas for submitting proposals for beam time. What's really nice is that an hour into that session is the deadline for people.
Yeah.
So this may be looking perhaps a cycle ahead of time this summer, but there is definitely room for some new ideas and some discussion to bring about some new science, whatever it is that you guys are interested in. And I always close with my kids because they're cuter than me for the most part. And yeah, we got the twins now have glasses, so my poor eyesight has caught up to them, thankfully. And my son chose glasses that look exactly like mine. So he's clearly going in the wrong direction in life. So that's pretty much all I wanted to like pre-prepare or anything like that. I don't want to monopolize too many things by talking, but that's the basic difference. I know that Tim was giving some information on how the monochromatic beam works, so I wanted to focus a little bit on the mechanics of the white beam and exactly how it is that we use those different than the mono beam. So that's it. And I also run a beamline at Brookhaven Lab. Okay.
Thank you, Matt.
Thank you.
Any questions? Yes, please.
What is going on when the beam is lost and how do you regenerate that?
When the beam is lost in the ring.
Yeah.
Okay. So I have nothing to do with it, first of all, especially when it's lost. That was not my fault. So what they do, I mean, it's an accelerator, basically, is what the building is. And there is a linear accelerator that gets electrons moving nice and fast, shoots them into a storage ring, and eventually they get into the big ring, which is the APS proper, and the electrons go near the speed of light. And what synchrotron radiation is when magnets change the direction of the X-rays, it goes, and it just shoots a whole bunch of energy out in the direction that it was traveling before the magnets made it go this way. So in the case of 13, where they have a monochromator, that hits that monochromator. The monochromator takes one nice beam at a particular energy and sends it down the pipe, and the rest of it just gets scattered off into the distance and blocked by lead or something else. What we do is we go, nah, I want all that. So we just get coming right off of it. So when the beam dumps, it means that the electrons that are in the ring, for some reason or another, are no longer circulating the ring. And that can be caused by a lot of different things. So there could be orbital misalignments and the X-rays literally crash, or I'm sorry, the electrons literally crash. And so they have to start the whole thing over again. Power outages are a thing. That's also a problem. So what they have to do again is start from scratch. They start speeding up electrons, send them through the accelerator, get them into the ring, and then get them into the big ring and running again. And that takes a lot of effort from a lot of different people. I am none of those things. So yeah, that's my dumb way of putting it. I think
That was helpful.
was it really?
And check this website and this ring status. So wait and check.
Yes.
And also sometimes if you are here, you hear the announcement, the beam down or beam resumed, enable shuttles enable those. If you hear shuttles enabled, and if you say this ring, you will say the blue, it's a current intensity. So make sure you have this on your cell phone, the website, and then you can check all the time. If you're not here, yeah. If you're here, if you're here, you will hear it. Yes.
Yeah, and it's really nice when we sit there,
Yeah.
you know, back at 6 p.m. because you'll hear. So it's really.
Really? Yeah. So that, beam loss is just like weather. It may happen. Bad weather, it may happen. Yeah.
So what happens to when beam is lost? Go get dinner.
Alice and Gremlins get to work, and when you come back, the magic returns.
In the granite melting experiment, how do you define what is the wet and dry sample?
You can measure it before and after.
So for the wet sample, do you soak it, or is it actively being soaked during the experiment?
We can ask Caleb about it later. I don't know if it's sampled at pre-contained water or if it's one that they had to synthesize with water. I don't know if you guys know the answer to
I'm
that.
pretty
yet.
sure I had pre-water in it.
Yeah, and then the
Okay,
dry
so-
ones, they just.
Yeah. Yeah, so it was a natural sample itself that already had water contained in it. Dry ones are easy. They're harder to control, but easier to make, I think, is the way to, because you just make it really hot. And it drives off any of the water that's on it. And if you have a temperature differential and an iron scrubber, you can actually suck all of the moisture, excess oxygen, everything like that out of the system. So it's very nice. And you can measure them before and after using iron measurements to see how much water is in the sample and where.
It's hard to detect it in situ.
Yeah.
If you are baking the dry sample to make it dry, are you not worried about any thermal microcracks during that process? Or
He'll tell you.
okay.
Dr. William. Sure he is.
Yeah. Yes, you can end up with cracks from that. The other thing you have to be careful of too is when you're starting with a sample like that one in particular, like you noticed, the biotite was one of the minerals
Yep.
that was dealt with there, right? So the method I just mentioned will destroy biotite. It will not be biotite anymore because you've actually structurally taken the water out of the biotite, right? So it actually breaks down and has different mineral phases there. So it depends. Your input is directly going to influence what your output is. So it depends. If you want to study a natural rock, which was the target of the studies that were shown there, they put them in kind of as they were. The most I would think the most that you would do is like 150 C in a vacuum oven to get the absorbed moisture off, but leave the structurally bound moisture in the sand.
Okay.